Hi everyone, we are going to do solving differential equations today. So this will be a two-part video to show you a few different examples and include some visuals to help you picture what is going on. Just to remind you, you have done things related to differential equations already. So let me just remind you here. You have already created a differential equation whenever you did whenever you did implicit differentiation. That whole process looked like this. This is whenever we started with an equation. It wasn't a function, an equation with x's and y's mixed up, and then you solved for dy dx. You did the derivative with respect to y that created dy dx. So this right here, this dy dx equals something with x's and y's mixed in. This is a differential equation. So you've created them before. You've also done basic differential equations whenever we did antiderivatives. So you've already seen things like, oh, y prime is x cubed. Find y. And then you did an antiderivative, but you only did them where you had to worry about finding the antiderivative of x's. There was really no y's involved, and we just went from y prime to y. Like you didn't think much about that. We're going to be thinking more about x's and y's, their antiderivatives. That's going to be the main difference for today. And also, we have been working with slope fields. Now remember, a slope field is just a way to visualize what a function, like the solution function, looks like. So you're given something like dy dx. Well, you're given something like this right here. And then you graph the slope field, and that helps you picture the mystery function, the original y, that goes through that slope field. So we're going to be looking at some slope fields today. Now let's talk about this. There are many types of differential equations, and we're only going to be solving the separable differential equations. I just want to show you something so you can see if you choose to, like I said, major or minor in math, you'll take differential equations. And so you'll do like basic differential equation. We're going to be doing first order or ordinary differential equations. There are partial differential equations. There's second order. That's whenever the second derivative is involved. We'll be doing separable ones. There are non-separable ones. There's like homogeneous, non-homogeneous, like I said. We won't do those. We're only going to do separation of variables down here at the bottom. If you take this class in college, there's Euler's method. We are going to be talking about Euler's method, but we're not going to be doing Fourier transforms or Laplace, anything like that. So what we're doing in class is very manageable, and I think you're going to find that it's not too bad what we are doing for the CALC BC curriculum. All right, so let's talk about like what is a separable differential equation. A separable differential equation is whenever you start with a function or a derivative dy dx. It's in terms of x's, y's. Sometimes it'll just be x, sometimes just y. This one is a mix of x, y, and you need to be able to separate it so that I'm going to make a note here. We will use, this is a star. We're going to use algebra. So the algebra skills you've known since middle school to put y's and x's on opposite sides of the equation. So the x's need to go on one side of the equal sign and the y's go on the other. So your dy needs to be with the y's and your dx needs to be with the x stuff. Generally, people put y on the left side and x on the right side. All right, so here's another thing that I want to point out. dx and dy must end up in the numerator. And let's just talk real quick, like why does it have to end up in a numerator? Well, think about it. Like what is dx even? dx, the first time you saw it, came from whenever we did Riemann sums, and we added up infinitely many rectangles, and we found the area of a rectangle, where we did base times height. And your height was the function value. Your base was dx, but remember, like your base was delta x technically, but we turned delta x into dx to represent that tiny, tiny width. So dx comes from base times height. You have to have base and height next to each other in the numerator. If dx is in the denominator, like you're not really representing area. It's not base times height anymore. It'd be like height divided by base. So just keep that in mind whenever you're doing this. Like what did dx represent originally? It was a base. All right, so let me just show you how this would work. I'm going to get here's y, here's y. I'm going to get my y stuff together, and y plus 3 are added, so they have to kind of stay together. Let's start by moving dx to the other side by multiplying each side by it. So then you have dy equals y plus 3 dx over x to the fourth. So my x's are together on the right-hand side, and typically people are going to keep the x's on the right, and they're going to put the y's on the left. So if you're going to move y, the plus 3 has to go with it. So let's divide each side by y plus 3 and divide each side by y plus 3. And whoop, that cancels over there. So I'm going to be left with dy over y plus 3 equals dx over x to the fourth. This is something that you could solve using antiderivatives now. Here's other separable ones. You could do some manipulation to get the x's together and get the y's together on opposite sides. So take a look at these and think about like how you would move those. Now, the non-separable, let's talk about like, why is this not separable? You could try and you could do something like, well, what if I subtracted y from each side? Then you have dy dx minus y equals x. So you got your y with your dy, but then I have to get the dx to the other side. And you could try multiplying each side by dx. But then you would have to technically distribute it here. It doesn't just cleanly cancel because of this y. So you'd end up with dy minus y dx equals x dx. And like your y's are together, but then there's still this dx. And you were like, oh, what if you were like, oh, we could divide by dx? Then you'd be going backwards to where you started from. So it's really this addition sign between the x and y. Sometimes if there's addition between x and y and you can factor something, you will be able to separate, but it depends on what you can factor. Like if I take x out, I have y plus x squared, and then I still have this addition between x and y. That's going to end up making it not separable. Again, here, if you have adding or subtracting between x's and y's, it's going to be hard to separate. You can still solve these. There are methods to solve non-separable. We're just not going to do them. Notice here, if you're thinking like, oh, hey, these are added, you're adding x terms together. So you can just keep these x's together, which you want anyway. And here there's addition, but it's addition between x and a constant, and constant can just be with an x or be with a y. So we will be separating always before we solve. So jot this down, and then we're going to move on to the basic steps, and I'll show you how to do it. So I would pause the video, get these steps written down, because these are what we're going to be following for the entire video. All right, so if we're going to solve a separable differential equation, like I said above, you're going to use algebra to always get the y terms on one side and x terms on the other. Always start there. What you're going to do next is you'll be able to take the integral of each side. So you've already done integral, so you're going to use your integration skills to do that. Pay attention to dx and dy. They're going to go away. You are allowed to do the integral of each side because remember, just like with algebra, you can like add 2 to each side or divide each 2 by 3. You can take the integral of each side if you do the same operation to both sides. All right, we're going to talk about this thing called the ultimate C. Some people call it the super C. Like, you know, when you've done an antiderivative, you always have to add C. Well, there's a little bit more involved, so we're going to talk about that here. That's how you get this super C. If you are given an initial condition, when I say more information, I mean an initial condition. So you might want to jot that down so you remember. Also, it's common for initial condition to be abbreviated IC. So if you have an initial condition, as soon as you do an antiderivative, you are going to find that C value. And then once you have your antiderivatives, once you have your C value, what you're going to do next is isolate y. You need to remember when you're solving a differential equation, what you're really trying to do is find your mystery function y. Like you're going to start with dy dx, and you're trying to find just what y equals. So once you've found what y equals, you're done. So like it says here, once y is solved for, you're done and you've solved the differential equation. Once it's in the form like y equals something plus whatever your constant is, and sometimes you'll solve for this C. All right, just so you know, if you take this class in college and your professor's solving these, they might switch steps 4 and 5. I generally am always going to do it in this order. And as we do these in class, I'll explain why. I think it leads to less errors, especially whenever you're finding your C value. I think it's better to find the C value first and then get Y alone. But we'll talk about that in class. But just so you know, you might see people switching the last steps whenever you're doing these with a future professor or watching a future video. All right, so let's go ahead and solve one. We're going to solve a relatively basic one. These can get pretty complicated. And so, yeah, obviously we're going to start with the easier one. Now, let's take a look at this here. I'm going to show you what this looks like on a slope field. So use graph slope fields by hand, which I'm sure you found to be pretty painful. Desmos is awesome because they have the slope field grapher. So you can go, we're going to be doing this in class. You can go to the slope field generator and you can type in what dy dx equaled. So dy dx was 8x cubed y squared. So I type that in here. They use a different notation. They don't do dy dx. The only annoying thing about for this one, for some reason, it's not graphing the whole thing, but I'm going to zoom in here and then it kind of looks like it graphed the whole thing. We're only going to care about the ordered pair 1, 1. So in this case, I'm giving you a differential, dy dx, a derivative. I'm telling you that the solution is going to go through the point 1, 1. So we're going to go through this point right around here where my cursor is. And you want to find the y value, the solution that does that. So the slope field is going to help us picture something here. We're going to graph it so you can actually see what it looks like. But just so you know, Desmos will graph you a slope field accurately and quickly, which is awesome. All right, let's go through our 4 steps here. Our first step is to get get x's and y's on separate sides of the equation here. So let's go ahead and do that. I have y and y, and then I have x's and x's. So I'm going to move my y's to the left-hand side here. So let's divide by y squared. And then I have dy over y squared equals 8x cubed dx. Okay, so are all my y's on the left? Are all my x's on the right? Okay, we're good to go. What I am going to do, though, is I'm going to rewrite 1 over y to the second as y to the negative second because it's going to make it easier to find the antiderivative. All right, step 2 said find the antiderivative of each side or take the integral. Take the integral of each side. So I'm going to write that integral sign down here because I already have it written. And then over here in step 2, I'm going to write down what the antiderivative is. So you see what I mean? This is different than what you've done because normally you were given like y prime equals something. Like you could do this problem and you just call the antiderivative y. And you would have said, oh, it's ax to the 4th over 4 plus c. This is old news. This is new news. Like, look, you have to think about the antiderivative of your y as well. You can't just call it y. So anyway, the antiderivative of y to the negative 2, okay, I'm going to add 1 to my exponent. It's y to the negative 1, divide by your new exponent. Oh, check it out. You did an antiderivative, so you need to put plus c. And then here, I just did the antiderivative here. It's 8x to the 4th over 4 plus c. Now, I'm only going to do this once. We're never going to do this in class because it's kind of like it doesn't matter. It's all going to be c. C is a constant, remember. Technically, this is your first constant, and this is your second constant. So then technically what we should do is get your constants together. So I'm going to do minus c1 minus c1. So let's keep talking about like what is really happening here. I'm going to make this negative because like dividing y to the negative 1 by negative 1 makes it negative. And then I have, this is 2x to the 4th plus a constant minus a constant will give me another constant, c3. But the thing is, like, we're not going to keep making more subscripts like c4 and c5. Like, all your constants in the end are going to move to the right-hand side and just become c, or like a super c, the ultimate constant here. So let's just go ahead and call it c. And anytime you add something to it or multiply it by something, it's just going to keep becoming a new constant. You'll just keep calling it c, okay? So I'm going to put this in the denominator here for a second. And I have 2x to the 4th plus super c. Okay, cool. So I have done my antiderivative. And at this point, I haven't really done too much manipulating. This is where I'm going to find my initial condition, given that my curve goes through 1, 1. Saying that I go through the curve 1, 1 is the same as saying the function at 1 equals 1. Okay, so let's take this here. And again, this is step 4 where I'm finding my initial condition. Okay, sorry. Anyway, that'd be negative 1 over 1 equals 2 times 1 to the 4th plus c. All right, so let's keep going here. 4th plus c. So the negative 1 equals 2 plus c. Subtract 2. Sorry, I'm running out of room. And negative 3 equals c. I subtracted 2 from each side. All right, so that means I can take my c value and plug it in for what it was. So now I have negative 1 over y equals 2x to the 4th minus 3. Okay, so I need to solve for y here. At this point, let's get y out of the denominator. So we're going to multiply each side by y. And then I have negative 1 equals 2x to the 4th minus 3 times y. And then we're almost done. Let's just divide by this here. 2x to the 4th minus 3. So, all right, what does y equal? I like putting the y on the left. So negative 1 over 2x to the 4th minus 3. Cool, that was your first differential equation. Let's graph it and see, does it even look like the solution that goes through 1, 1? Okay, go to decimal. So what was it? Negative 1 over 2x to the 4th minus 3. Let me make sure I have that typed in. Negative 1 over 2x to the 4th minus 3. And I'm going to call this y. It's not dy dx. It is y. Turn this thing on. Okay, yay, look. So this is my particular solution that goes through 1, 1. And look here, at 1, 1, you can see this curve does go through it. It follows the flow of the slope field. And the slope field, the lines are super vertical and you didn't graph it yourself. So it's kind of hard to see, like, does it actually go through the flow of the field? This one's harder to see. We're going to do one that's a lot easier to see. But this is an example of a function going through the slope field and going through the initial condition. And you know what else? If you find the differential equation with the c value, we're going to call this a special name, and you need to know this. It is called the particular solution. That is opposed to whenever you just find a general solution where you don't know what c is. Like if you were just to solve for y at this point, that would give you a general solution, where your general solution would still have a c in it. So it still has c in it. So your particular solution is whenever you solve for your c value and it's just one single curve that goes through the slope field and goes through that initial condition. All right, cool. I'm going to give you a u-try to do, and then I'm going to end the video and do one more example in a second video. So here you go. I want you to solve dy dx equals 2y squared if you go through the point 0, 3. So try this out and do the 5 steps, and we'll compare your answer in class. So let me stop here and let me pick up in a new video.